Welcome back. In the last video, I revealed the big surprise, Food Vision Big, that we're going to be working on to complete this milestone project 3, PyTorch model deployment. And so by the end of this section 10 and 11, we're going to have an equivalent demo here of Food Vision Mini, but for Food Vision Big, a model capable of classifying 101 different classes of food. So let's go here. You might have already created this. In the last video, I challenged you to use our function create EffNetB2 to make a model capable of fitting 101 different classes. So I'm going to call mine EffNetB2 Food 101 so that we know it is capable of fitting 101 different classes. The transforms are going to stay the same. So I'm going to write down here, create Food 101 model and transforms. Now, the beautiful thing, thanks to our function that we wrote before, all we have to do is set number of classes equal to 101. And let's now get a summary. I'm going to find summary in the notebook. I'll go, we've done this a few times. Yeah, I'll get this one. This is from right up the top here, EffNetB2 feature extractor. Come down, let's print a summary to make sure that this model is capable of fitting 101 classes. So Food 101, there we go. I'm just going to make a bit more space over here. So we have the same input shape, and there we go. Look at the output shape, 101. That is, of course, because we set num classes equal to 101. And just as we want, all of the base layers are untrainable, so they're frozen, except for the output layer here. We have a sequential classifier which has 101 output classes, which is exactly what we want for Food 101. And now, you might notice that there's a lot more parameters here in the final layer than our previous model. Now, why is that? Well, that's because we've got 101 classes rather than just 3. So if we copy this code down here, and if we go, instead of EffNet Food 101, we want EffNetB2. So this only has 3 output classes, so therefore only has just over 4,000 trainable parameters. So of course, more output features in the final layer equals more trainable parameters. So we've got our model. Now we might do one thing to adjust the transforms. So let's have a look at this. EffNetB2 transforms. What we might do is add in some data augmentation to this transform. Now, why do I say that? Well, let's have a look at the Food 101 dataset. So Food 101 torch. This is what we're going to be doing, downloading this dataset. And so we're now going to step things up and working with over 100,000 images. Whereas previously, or in fact, spoiler alert, we're going to only use a subset of this as well to keep our experiments quick. If you'd like to experiment on all of these, I would 100% encourage you to do so. But when we're working with such a large amount of data, it's a tendency for our neural networks to overfit. So if we go to learnpytorch.io, what is overfitting? Number 4, I believe, is where we covered that topic. And then number 8, overfitting, right? So the training loss ends up being lower than the test loss. So that's overfitting. That's because we have so much data that our model is learning the training data set too well and not generalizing to the test data set. But of course, we have some techniques to deal with overfitting. And the most common technique of preventing overfitting, well, the technique is known as regularization. So you want to regularize your model. And I have a little bit of trouble saying this word. But here are some ways that we can regularize our model, get more data, simplify your model, or use data augmentation. This is probably one of the easiest ways, aside from transfer learning. We've already seen this in practice. This is what we're already doing. But why would we use data augmentation? Well, these are some things, tricks of the trade that you kind of pick up along your journey in machine learning. And one of the ways to do so is read how other people have done things. So this is from Torch Vision, the Torch Vision team, how they trained their pre-trained models in the Torch Vision package. So if we scroll down here, they have a list of techniques that they used. And so here's a fair few. We're not going to go through all of them, but there's learning rate optimizations, trivial augment. So this is what I mean by data augmentation. We saw this way back in maybe section 4 or section 3 using trivial augment, but now we're working with such a data set, we're going to reintroduce it. Long training is another option if you wanted to try training your models for longer. We've seen that before. Random erasing, label smoothing, we're going to see that one later on, that's a spoiler. Mix up, cut mix, weight decay, fixed res mitigations, exponential moving average, or that maybe not exponential, is it exponential? Yeah, it is, exponential moving average, wow. I know a few more acronyms than I give myself credit for. And then inference resize. So of course, I'll let you read through this, but let's come back to here and I'll write a little note. Since we're working with a larger data set, so this is where your mind should go. We may want to introduce some data augmentation techniques. And of course, we could try to train our model without data augmentation first, but because this is a machine learning cooking show, I've tried this and I found data augmentation helps. You could try it without. So we may want to introduce some data augmentation techniques. This is because with larger data sets and larger models, overfitting becomes more of a problem. Not always the case. Again, a lot of the statements in machine learning are quite general and they take some experimentation. So because we're working with a large number of classes, let's use trivial augment as our data augmentation layer. Beautiful. Or as our data augmentation technique. There we go, that's probably more precise. And then for a list of state-of-the-art computer vision recipes, now of course this is computer vision specific, but what you'll often find is there are a lot of these style recipes for many different problems. So for natural language processing, you would still ask the same question, can we use a pre-trained model? Are there forms of augmentation? And pre-trained models for natural language processing, you'll probably find on Hugging Face Hub. But we're getting beside the point here. We want to work on food vision big. So let's do that. We can adjust our transforms by going food 101 transforms equals torch vision dot transforms dot compose. And I'm going to put in a list here. We will use trivial augment wide first. So torch vision dot transforms, and then this is trivial augment wide. Beautiful. So let's now see what this looks like. Food 101 transforms. Wonderful. So that's going to be our training data transform. So create training data transform. Because we've got way more classes and way more data, we introduce data augmentation so that hopefully our models don't overfit. We'll see this in practice later on. And then of course, I might just print this one out up here. And then for the testing data, we're just going to use the original EffNetB2 transform. This is our testing data transform because we don't we don't want to augment our testing data or inference data. So recall the purpose of data augmentation, if we go back here, is to manipulate the training data in a way so that it's harder for the model to learn as it artificially adds more variety to the data. So it does that by manipulating the input images. So there's some transforms and a model ready to go. What do we need next? Well, we need a data set for food vision big. So I'm going to write down here, getting data for food vision big, and you might want to give this a shot. The class that we're going to use is from torchvision.datasets. We're going to download the whole Food 101 dataset to our Colab notebook. So get the Food 101 dataset, give that a shot, and we'll download the biggest dataset we've worked with so far in the next video.